I was driving, taking my daughter back to school, to her apartment, not she's done with school, her apartment in Boston, and the traffic suddenly stopped, so I hit the brakes, and her stuff goes sliding. I had a van there, the stuff goes flying, everything moves forward. Well, why did it go forward? The reason the boxes, everything, the table, the chair moved forward, we have something called momentum. The object, all the boxes sitting in the car, if this is sitting on top of the car and the car is going 50 miles per hour, that object is going 50 miles per hour. Once the car stops, that object wants to continue going 50 miles per hour. Sometimes it goes, sometimes it doesn't. Why does it go? If it goes, because the friction force on the bottom is not strong enough to keep it from going forward. So linear momentum, it's momentum due to an object that's moving, and it's a vector, it's equal to the mass times the velocity. Mass times the velocity. When you drive home today, you can try it. Take your book, put it on the front seat of your car, especially if you have like a book like mine, looks like shiny, smooth surface there. And if you go in 55, 65 on the highway, slow it down to 55 quickly and see what will happen to that book. Will continue to move. And again, the reason is linear momentum. The units for linear momentum, if you look at it, what are the units for mass? Kilogram. And what is the unit for velocity? Meter per second. So momentum has units kilogram, meter per second. We use P, the simple P, for linear momentum. Now, you probably don't, maybe you're too young to remember this, maybe you weren't even born. Do you know East Longmeadow, that crazy rotary there in East Longmeadow? It's supposed to be one of the top 10 most dangerous rotary in the world, actually. Right there's a baseball, softball field. And a few years back, could have been 15, 20 years ago, there was a game going on and two sisters driving a car. And a trash truck came and hit them and killed them both. And people wanted to know how fast that truck is moving. You know, the damage that truck made to the cars. The driver must be going at least 80 miles per hour, 90 miles per hour. I'm going, it doesn't have to be that much. So imagine now, if you stop, I'll give you two stories. If you stop at a stoplight, there's you, and you are now moving. That's you. Red light, right here. So you're not moving, your velocity is 0. A car comes from behind you. The car is a small car, well, not a small car, a medium-sized car, 1,000 kilogram, 2,200 pounds. An average car like sedan, we're talking about maybe a Honda, Toyota, Camry, Honda Accord, Kia car, one of those cars. And the car is moving at 30 miles per hour, so 30 miles per hour. What's 30 miles per hour here? 30 divided by 2.24. That's 13.4 meters per second. And if they hit you there, you're going to go across that intersection. But how much moving power does this car have? That's what linear momentum is, power, moving power. How much power does it have? It's the mass times the velocity. What was the mass of the car? The mass of the car is 1,000 kilogram times the velocity, which is what, 13.4. So that's 13,400 kilogram meter per second. Now again, we'll change the story a little bit. We'll use a dump truck there or an 18-wheeler. There's you again. Your car is now moving. And instead of now You got a big truck coming from behind. Now that truck has a mass, instead of 1,000 kilogram, probably 15,000 kilogram, 10,000 kilogram. So it's not light if it's loaded there. And has the same speed, going 30 miles per hour, which is 13.4 meters per second. What is the linear momentum will have to be for that truck? 15,000 times 13.4. Which is what? 201,000. Look at the difference. 201,000. Versus 13,000. So when this truck hits that car, the damage the truck is going to do much, much worse than that car hitting, even at the same speed. Let me rephrase the question. At what speed we want this car to go to create the same damage as this truck? Maybe you'll see it better that way. So how fast we need this car to go at and hit you to create the same damage, the same linear momentum as this truck? So now I'm looking for the speed. I said I want the mass times the velocity of the car to equal what? 201,000. And the mass of the car is 1,000. So the speed of the car has to be what? 201 meters per second. Ready for this number? How fast you want that car to go? The car will have to go at a speed of 450 miles per hour. So if you take that car and somehow you manage to make it run at 450 miles per hour and hit that car, that's how much damage, how much linear momentum we'll have when you equal to this one. 450 miles per hour. You know, if a car gets hit at 450 miles per hour, probably nobody's surviving. Now, if you think that's a big number, by the way, the truck, you ever watch a video where a car is stuck on a train track? The train comes in, hits it. The car looks like a box of matches, just goes flying like nothing, or the bus goes like nothing. Why? Imagine the mass of that train. Or a plane, when a plane hits, like the 9/11 incident. That plane was fully loaded going 500 miles per hour. How much power, moving power, does it have it? Add to that, the fuel is going to burn. And how much damage the fuel is going to do. We saw the effect of that on 9/11. Those planes, the 747 or the C-5 that you see in Westover flying over, when they're loaded, I forgot what is, I can research that quickly, because I heard the number one time, and it's like mind-boggling, the mass of it. What is the mass or the weight of C-5? Maybe I should write plane, because maybe they don't know what C-5. Plane when loaded. Let's do a 747. Because 747, C-5, I'm getting C-5 Galaxy. How much does a Boeing 747 weigh? There we go. There's a number for it. Let's see if we can get it. How much does a Boeing 747 and a 777 weigh? Can you see the numbers? 970,000 pounds. 747 fully loaded, projected to be 970,000 pounds. So divide that, 970,000. Oh, let me just switch back here. 970,000 divided by 2.24. That plane weighs 433,000 kilograms. 433,000. This is 15,000. So compare that to, so a 747 has a mass, when it's fully loaded, 433,000 kilograms. Not 15,000. Going at speed, velocity of 500 miles per hour. When they're cruising, that's their speed. You do the math there, you get an idea how much power on those planes. We thought that truck is really big, 201,000. Look at the power for a 747. Its mass times the velocity. Now the 500 miles per hour, 500 divided by 2.24, it's going at 223 meters per second when it's cruising. So that's 4,033,000 times 223. Ready for that number? 9,655,9,000. 96 million. 96 million. That's why when you see some of these accidents, sometimes when a plane falls out of the sky and we go look at the damage, sometimes you see the TV there, everything is burned, first the fuel, but the damage it creates there, there's no house going to stand the way, there's no roads going to hold it. There is a lot of power on that plane. Not many buildings can hold that much actually moving power. Now again, power is a vector. So let's look at this story here. We're going to change the problem a little bit here. Sometimes you go to the pond and you see all these ducks floating, geese and duck in the pond. There you throw a piece of bread there. So there's a piece of bread. Now we got a duck coming to get that piece of bread. Here comes the duck. It's moving this direction. This duck, duck 1, we'll call it D. D1, duck number 1 coming from this end. Duck number 2 coming from this end. And we have what? A geese going from that end. A duck has a mass of 4 kilograms. So this is 4 kilograms. This duck is also 4 kilograms. This goose is only one of them. I had a plan to have 2 geese there, but one of them, it's 9 kilograms. They're bigger, fat, heavy. And they're all paddling, going crazy. They want to get to that piece of bread that you threw there. Now, these ducks can move at a speed, velocity of 1.10 meters per second. Velocity here, 1.10 meters per second. But the geese here, or the goose, we have one only, I keep saying geese, one, has a velocity of 1.30 meters per second. A little bit faster, heavier and faster. And the question, find the total, we're looking for the combined linear momentum. Again, linear momentum is a vector. So if I do a free body diagram, everyone see the story, what we're making here? We have two ducks and a goose fighting over a pico and third a piece of bread. So each one of these have a momentum because they are moving. So duck 1 is going to have a linear momentum going in this direction. It's a vector. It's the same direction as velocity. It's moving that way. So this is the linear momentum for duck number 1. Duck number 1 is going to be the mass of that 4 times the velocity is 1.10. So that's what this one, P1, linear momentum 1, is 4.40. It's coming down. Let's look at duck number 2. Duck number 2 is going to have a linear momentum going in that direction. Notice duck 2 is going to the right, which is also 4 the mass times the velocity. And the goose here is going upward, is going to have a linear momentum in that direction. It's the mass of that, which is 9, times the 1.3. $11.7. And now I need to find the net result, the equivalent. We actually get how many vectors? 3. We try and find the net result. We can do it mathematically, we can do it graphically, the way we did vectors before. You can draw them in directions, just keep adding to them and you get the result. If I do these graphically, I'll do them both ways. I think I still have a graph paper sitting here. The good news, they're all like perfect. They go straight up, down, left and right. I don't need to use a protractor. And it doesn't matter which one you draw first. So if you want to do duck number 1 or P1 first, notice P1 is going which way? Down 4.4. So let me go down 4.4, each box here. I'll do 4, here we go, centimeters. That's 4.4. I am going to need the protractor in a second. This is P1. Notice it's 4.4 down. That's what's going down. Add to it P2. So from the end of this, when you're adding vectors, from the end of this, we're going to add P2. P2 is 4.4 to the right. So from this, let me go 4.4 to the right. So 4.4 to the right. Now, from the end of this, I need to add vector 3, which is 11.7 up. So 11.7 up. That's 5. Somewhere there, 6 and 7. That's P3. Twist it a little bit there. You can see mine is moving in the line. So what's the result? The result is going to be this vector from the origin, where we started from, to the final spot. That's my resulting vector. And I'm measuring the length of it. It's almost 8.5. So this is 8.5 centimeters, which is 8.5. And I need to measure the angle. I might be off by a degree because I see my line is already on top of that circle. Let's see what that angle is. Roughly 60 degrees, right? At 60 degrees. So the resulting vector, P total here, is going to be 8.5 at an angle of 60 degrees. Just like we added forces before, remember? Same way we added vectors. Nothing changes. Now, if I want to do this mathematically, this is graphically. I'll leave it there in case you're still writing. We're going to do this mathematically now and see if the math agrees with us. When you're adding vectors, we go back the way we did it in chapter 3 or 4. And that's what? We make the table, we write vectors, we find the x and y component, we go through the math. Here's the first vector, I got 3 of them. Second vector. Third vector. So let's write the vectors here. X component, y component. Does that look familiar? Now we're kind of reviewing for the final exam. X component. To get the x components, what? R times cosine theta, in case you forgot. And the y component, what was it? R sine theta. You always want to write the vector with respect, the angle with respect to the positive x-axis. So you look at vector P1. It's 4.4, and what's the angle? What's that angle?
90.
Try again.
What angle?
This angle.
0.
Nope. From here, measure it from here. What is it?
270.
Rebecca's 270. Yep, I could have said negative 90. I was looking for the negative. Because you're going down. Or, as Rebecca says, plus 270. 270 or negative 90 is fine, but not a plus 90, because that would make the x and y positive. The second vector, P2, is going to be 4.40. What's the angle there? Here? 0, good. And vector P3, which is 11.7. And what's the angle for the third one? 90 degrees. Now we're going to find the x and y value for each one. This will be 4.40 cosine 270, and if you do the math on your calculator, that's a 0. 4.40 sine of 270, which is negative 4.40. 4.40 cosine 0 degree, 4.40. 4.40 sine 0 degree, that's a 0. 11.7 cosine 90 degrees is 0, and 11.7 sine of 90 degrees is equal 11.7. So we wrote the vectors. I found the x and y component for each one. The result in the x direction and the result in the y direction. The linear momentum in the x direction is equal to what? 4.40. In the y direction is going to be 11.7 minus 4.4. 4 from 7 is 3. What's 4 from 11? 7? If you want to write it in rectangular mode, you can say the total is equal to 4.40 in the x direction. Remember that notation? Plus 7.3 in the y direction. That's what the result is. It has an x and a y component. Since they're both positive, which quadrant? Are we in quadrant 1? Yeah. We're in quadrant 1. Can we find what are the length of that vector and the angle? Because I'm trying to see if my graph is good or not. I'm trying to see if we did it right. I came up with 8.5 angle 60. I should be somewhere in that neighborhood if I did it right. So what is the value of r? That's the magnitude of the vector. It's to take the x value, square it, add to it the y value squared. You take the square root of that. $8.5. 8.52. My picture says 8.5. Let's see if the angle is 60 degrees. If I was right too. To get the angle theta, it's always the inverse tangent of the y value, which is 7.3 over the x value. And now let me make sure, because I use the calculator all the time, let me make sure I'm in degree mode. Yep, I am in degree mode. Clear, here we go. The inverse tangent of 7.3 divided by 4.4. 59 degrees. And my picture says what, 60 when I graphed it? Yep. That's what the result. So what is the total linear momentum? If you want it, you don't want it the x and y coordinate, you want it in terms of r and theta, is 8.52 at an angle of 59 degrees. That's linear momentum. I'm not done with it, but that's what the definition of linear momentum is: mass times velocity. But let me play with the math here. And I'm going to play with the units. Let's go back to Newton's second law. It says the net force equals what? Mass times acceleration. Let me put the linear momentum here. Is mass times velocity. Let me look at the units again slowly. Mass is what? Kilogram. Velocity is what? Meter per what? Second. Kilogram times meter per second. Let's look at the units here. It's mass. Acceleration is what? Meter per what? Second squared. There's a difference between them. The units don't match. But what will happen here? Watch the math now. What will happen if I multiply both sides? Because that's an equation. You can't just leave it alone and go, okay, I don't know what to do. If I multiply one side by t, I got to multiply the other side by t. I have to. Whatever you multiply this side by, you got to multiply this side by the same thing. Why do you think I'm multiplying this side by t? What's the reasoning behind it? Well, what is the unit for t? Second. Mass is kilogram here, right? This is kilogram. Looking at the m here. I wrote m for mass, but the unit is kilogram. Now let's play with the units here. Let's do some algebra on that. So the units for this becomes what? Kilogram times meter times second over second squared. Well, one of these seconds will cancel this one, because there's two of them in the bottom, and you end up with what? Kilogram times meter divided by what? Second. Isn't that the same as this? So what I'm trying to do is prove here that if you want to actually calculate the momentum or the change in momentum, it looks to me like P equals what? It looks to me F times T. Unit-wise, the units of this matches the unit of this. And the equation where I'm going after is the change in momentum. Change in momentum is equal to the force times the change in time. What is a change in momentum? Is the final momentum minus the initial momentum. And here's my equation. The mass times final velocity minus mass times initial velocity is equal to F times T. That's the equation I was trying to derive. Or the change in momentum, the one above it, is equal to force times time. Now the only thing when we say force, we're talking about the average force, because the force might be a variable, meaning what? If I'm a baseball player, and you can see that ruler there, and assume this ruler actually is the bat here, and there's the ball. The ball comes in, there's no contact. Suddenly the ball touches the bat. The force now, before that, the force between the bat and the ball was 0. Once it touches that, there's a force. And as the ball keeps going, it's going to increase that force till the bat bends a little bit, or the ball bends a little bit. Then what will happen? It will stop, then they go backward. The ball goes backward in that direction. If you ever watch actually a baseball hit in slow motion, this is what you notice. For a picture. The ball comes in, the bat actually bends just a hair. The bat is tougher, harder than the ball there. It bends, goes backward just like a club in baseball. If you watch on a slow motion, when Tiger Woods just take a swing, you look at the club and the club is bent like this when it hits that ball. Then that becomes like a loaded spring. Boom, and the ball goes flying. That's what happens to the bat. It becomes like a loaded spring, so is the ball now. So the ball keeps denting till it stops moving, then it goes backward. So if you're watching the force actually between the bat and the ball, if you watch that force, this is what you see versus time. The ball let's say the ball is going to touch the bat right here. So before that, there's no force. There's no contact between the bat and the ball. Once the ball touches the bat, that force starts to increase. It goes to maximum value, then starts to decrease, then it goes back to zero. Once the ball leaves the bat, it's no longer in contact, the force between them is zero. So when we say, what's that force? Well, we can't use the force. It changes all over. We have to use an average force. What do I mean by an average force? If I was to calculate this area, what height can I use here? I'm looking for a height that if I treat it as a straight line and calculate the area of this will be the same as the red area. That's what I mean by the average force. So you'll see us right here, AVG, which means average, because the force is really variable. It's not constant during that impact. In baseball, in golf, in any sports, when you hit an object there, that force is changing, and the impact time is really, really short. We're talking about 1,000th of a second. When that ball hits the bat, it might be 1 or 2,000th of a second. Boom, and it's gone. Now you hear the sound. By the time you hear the sound, the ball is almost in the outfield. Why are we interested in this equation? Because we have a new term called impulse. An impulse did our book talk about impulse? Let's see quickly. Yes. We use the letter I for it. That's also a vector. So the direction of that, when I say vector, the direction of it is the same as the direction of the force. It's the force, the average force, times the time. Change in time. Anyone knows what the units for impulse might be? Well, let's think about it. Impulse is force times delta t. What's the unit for force? Newton. What's the unit for time? Second. So the unit for impulse is going to be Newton second. If you don't like the word Newton there, remember F equals ma. The mass is what? Kilogram. Acceleration is meter per second squared. So the unit for that is kilogram meter per second. Why? Because you're going to multiply that force, the Newton, that's what a Newton is. You're going to multiply it by second, you lose one of the seconds here. It is the same as impulse. Remember, F times T is the change in linear momentum. Momentum is kilogram meter per second. Mass times velocity. So that's really what the unit for impulse to. It's a Newton second or kilogram meter per second. Let's take an example with impulse here and change momentum and see how big that force between them. I'll start a new page actually. I don't know if you watched the Red Sox yesterday or not. First pitch, and Buchholz was pitching. Boom, home run. So here's Clay Buchholz pitching, throwing the ball to the batter. The ball is coming in at, I don't know, let's give it a speed of 92 miles per hour. It's coming this way, the ball. It makes contact with the bat. Then when it hits the bat, it goes back in that direction, and let's say at 95 or 100 miles per hour. Now, a baseball usually weighs about 140 to 150 grams. That's how much the mass of the baseball. So the mass of the baseball, we'll say 145 grams, which is 0.145 kilogram. Most baseballs between 140 and 150 grams there. The impact time, trying to think what might be, let's say 2 milliseconds. 2 milliseconds, which means in terms of seconds, 0.002 seconds. Milli, 10 to the minus 3. Usually the impact time is about 1, 2, 3 milliseconds of different tennis, baseball, hockey, golf. When you hit them, the impact time is really short. The question, what's that average force? I gave you the speed and the mass of the ball there. Well, let's watch that ball. We know the change in momentum is equal to average force times the time. And the change in momentum is what? The final momentum, mass times, well, let me just write it this way first. I'll come back and write the equation. It's final momentum minus initial momentum equals F average times the time. And what is the momentum? It's mass times velocity. Now let's look at this. What was the mass of the baseball? 0.145. What was the velocity or the speed of the baseball leaving, final, when the batter hits it? That's 100 miles per hour. How many meters per second? 100 miles per hour. 100 divided by 2.24. 44.6. .145. What was the initial speed going in? Let's convert the 92. 92 divided by what? 2.24. That's 41.1. So what are you going to write there? 41.1? What do you think? Notice I left a space in front of 41 intentionally. Why? Which way the ball leaving? Going to the right. That's positive. Which way is coming in? Going which direction? Left. That's a negative. It's a vector. Momentum is a vector. The direction of momentum is going to be the same direction of the velocity. The object is moving. Here you're going to the right, your momentum to the right. This is coming to the left, your momentum to the left. So one is positive, one is negative. So now we do the math here. Minus and minus becomes addition. And we know the time, which is 0.002. So if I do the math here, is 12.4 equals F average times 0.002. You got to add them. Minus and minus, that's a plus. You'll be adding both of these numbers. So to find the final average, what do? Divide by 0.002. And it's 6,213 Newton. That's the average force between them. If you want to know how much that force is, go to the gym today and have somebody do about 1,400 pounds of weight. You don't want to drop them on you, we don't want to kill you. But have the person lay on your back, have the person put the 1,400 pounds of weight on your stomach. That's what that is, because 1,400 pounds, if you divide them by 2.2, is equal to 634 kilogram. If you take 634 kilogram, multiply it by 9.8, you're getting 6213. So again, taking 634 kilogram and have somebody stack them on your chest. Unfortunately, we didn't deal with kilogram, so you multiply it by 2.2 pounds. If you go to the gym, you know what a 45 pounds looks like. It's heavy. So if you want to know how many of these 45 plates, divide that by 45. How about you stack 31 plates of 45 pounds, that big round one, on top of you. And whatever that pain that you feel, that's the average force between the bat, when Ortiz hits that ball, between the bat and the ball there. So it's not a small force. We'll do one more example, then we'll do conservation momentum. We are lucky because God gave us some instinct, like when we jump from a chair. If you jump, you always tend to bend your knees. Now, nobody told us to bend our knees. Nobody came when you were inside your mommy's tummy and says, hey, when you jump, bend your knees. You know, be careful. And the reason you want to bend your knees, if you don't bend your knees and you jump from this desk, you'll see when we do that example, you have no knees left there. Shattered. We'll see how much force there is. So we have a 72 kilogram. Well, let's say we just finished watching the NBA. LeBron James wins his third ring there. So he was like thrilled. Everyone was jumping. So we'll take a 72 kilogram player. Jumping up and down, excited about winning. Now, the way you jump, you bend your knees and you push yourself up. So the initial speed going up there when you jump, we have a speed of 2.1 meters per second. Now, what we need to calculate is, let's calculate the impulse. Find the impulse. So initially you're standing on the floor. Initial speed is 0. You're standing on it. Then you jump upward of a speed of 2.1 meters per second. That's what we have. So the impulse is change in momentum, or F average, if I know either one, times t, because this is equal to this. If I know what the average force is in the time, I can use that. If I didn't know that, I'll use the change in momentum. Well, my change in momentum is mass times V final minus mass times V initial. So the mass of the person here is what? 72 kilogram times the V final, which is what? 21 meter per second minus 72 kilogram times the initial speed velocity, which is what? 0. So what's 72 times 21? Oh, 2.1, not 21. 2.1. Is that 151.2? Kilogram meter per second. It says find the impulse. We did that. Let me change the story a little bit here. Now, if the person bent their knees, you're going to bend your knees. You're going to push upward. Made contact with the ground. For, I don't know, pick a number, 0.3 seconds before they jump. They bend their knees and jump. So you bend your knees, and when you jump, that time you release, like your knees become spring-loaded. You take off there. That time was 0.3 second. Can you find the average force? Let's see. Change in momentum equals F average times T. Change in momentum, we calculated that. It's 151.2 F average, that's from the top part, from here. We know the time was 0.3. So what's the average force? $151.2. Is it 504 Newton? So the average here is 540 Newton. And this force will be which direction? In the y direction. So if you want to write them as a vector, you go, oh, that's 4, not a y twice. 504 in the y direction. That's the ground pushing up on you. Is this what the ground pushes on you? Not really. This is the additional force the ground pushes on you. Remember, when you're standing on the ground, your weight is down. Mass is 72, gravity is 9.8. That's 705. And if you're not jumping, if you're just standing there, the ground is pushing up on you of how much? 705.6. This value is the additional force by bending your knees and pushing up. That's an additional force in this direction of 504, pushing up. That's why you went up in the air. Notice the force in the up direction is larger than the force down direction. If you're not bending your knees and jumping, I'm standing right now. I'm pushing down on the ground of 705. The ground is pushing up on me of 705. Once I bend my knees and I jump, I went up in the air. That means there's an additional force. That's additional. And where it came from is my knees actually become like spring-loaded and pushing me up there. Just like when you compress a spring and you let it go, you go up in the air. That's what happened. That's an additional force pushing upward. I'm not done with this video, but I can see you're tired, so let's take a break.